So this talk is about WTF, WebGL The Fundamentals. So it's not going to be as easy swinging as most of the other talks I do on WebGL, because this is going to be sort of like the backbones or the bare bones WebGL experience. It's not going to be a higher level framework. If you're interested in more higher level frameworks that allow you to get results quickly, then I highly recommend A, using a framework that I'm going to list later on, and B, probably watching the talk I gave at WTF, where I talked about the higher level frameworks for WebGL, for 3D graphics. So this is going to be a very fundamental introduction into what WebGL needs you to do to actually work and get graphics on screen. So this is the pipeline that we have to deal with, and there's a lot of words on it. There's so there's this box that says Vertices. The fuck is Vertices? Then there's a buffer. What? Then there's a Vertex Shader, then there's a Rasterizer, then there's a Fragment Shader, and then there's pixels. Okay, pixels we know. Right? Hopefully. If you don't know pixels, these little points that make this screen look like something is actually a pixel. Each of them is a pixel. And then we have shader code down here, and we have 3 different colors. Theoretically, on this beamer, we have more or less one, which is the blue one here, because that runs in JavaScript. So this stuff happens in JavaScript. Everything here, everything in green, happens on the graphics card. And then there's this weirdo, which is red, which is a piece of code that we write, but it runs on the graphics card. And it's not written in JavaScript. No, sorry, no JavaScript on the graphics card. It's written in a language called GLSlang, GLSL, GL shader language. Okay, now let's have a look at what the hell these boxes mean. First box, vertices. What the hell is a vertex? It's just, how do I put this? People who are involved with computer graphics, and in particular involved with the mathematics of computer graphics, love to invent new words because it makes them sound smart. So they invented a new word for a point. So because it's technically not a point, first of all, it's a point in 3-dimensional space, and second of all, we use it to connect dots to triangles, and triangles, each dot in a triangle, so each corner of a triangle has a similar characteristic, which is it connects 2 lines. If you think about it, if you have a triangle from there to there to there, this thing has 2 lines going into it, this dot has 2 lines going into it, and this one also has 2 ones going into it. So the proper term for a point that connects 2 lines is a vertex. And because English is a wonderful language and hates everyone and everything, it has a very weird plural form. So if you have 1 vertex, that's easy. But if you have 2, then it's called vertices. So 1 vertex, 2 vertices, just points. Okay, cool. So we have a list of points. That's easier than vertices, right? Now what is this buffer? Well, very simply put, it's an array. But it doesn't live on the CPU side of memory, it lives on the graphics memory. So it's nothing else than a piece of memory, an array where we can store things in. But it's called a buffer because it's a specific kind of array and we have to create it. Okay, sweet, so that makes it also easier. So we have a list of points that goes into memory as an array onto the graphics card. Okay, fair enough. Now the next one is a little tiny little more complicated. It's a vertex shader. Vertex. So it's about points. So what a shader is it's a program that runs on the GPU. Why would I want that? Well, the GPU is very, very specifically made for doing graphic stuff. So it's really good at providing you with a bunch of mathematical functions that you do not have in normal programming. It also is actually really, really good in optimizing these few operations that it has to do. So it is really, really fast in doing these operations. So you want a program that is specialized on getting graphics onto the screen. And this is what a shader does. So basically what we have here with a vertex shader is a program that allows us to manipulate the point that we are looking at. Why? Well, because memory access is actually quite expensive. So what we do not want is we do not want to change the memory all the time. So we have our 3 points, for instance, for a triangle, we have 3 points in memory, but we want to make the camera go away. So the points have to get closer to each other. We could totally do that with JavaScript and rewrite the array and then re-upload it to the graphics card, but that's actually pretty slow. So a better way of doing this is using a vertex shader. So what we're going to do is we have our 3 points. We do not touch the memory. The memory stays the same. The values in the memory stay the same, but we have a program that takes a value from somewhere, from thin air, that tells it how far away the camera is. And if we increase that value, it's going to draw the points closer together. So we have not touched the memory, but we have still changed the way it looks on screen. And you can do all sorts of things with that. You can do perspective. As I said, if I move further away with my camera, the points should go closer together until they disappear. If I move closer, then it has to come in. If I rotate my camera, they have to rotate. All these kinds of transformations can happen in the GPU without touching the memory, which is amazing. And it's actually really, really fast because it has no concurrency. It can run in parallel. Concurrency means and you actually just basically move these points around, but you do not like, oh, when this point moves there, then I move. This doesn't happen. So you can actually run the program multiple times, and graphics card have like thousands of cores, so they can run thousands of points at the same moment. So that is a vertex shader. The simplest vertex shader is taking the point and just putting it on screen. That's the easiest vertex shader we can get, because we have to have one. You have seen the pipeline, we need one. So the simplest one is just a function that takes the point and just puts it onto screen. Sweet. So now we know that we have a program that takes a point from this list of points and gives us a new point that will be displayed. Okay, cool. Now the rasterizer. Rasterization is needed because the world isn't perfect. Who knew? So theoretically, we have perfect lines between our points, wherever these points are. Unfortunately, in reality, we have pixels, and pixels are not allowed, or are not allowing us to give perfect lines. So what this thing does is that basically the rasterizer figures out which pixels it has to touch to get lines as good as possible, and then what we have to color in and how much we have to color it in. Let's have a look at an image. So here we are having our perfect line between these 2 points. And we can already see that it touches multiple pixels, but it only touches this one slightly, and this one slightly, and this one slightly. While this pixel is certainly in the middle of it, this one is only part of it is actually part of the triangle. So do we have to calculate this? Like where we have to color in and which one we don't have to color in? No, we don't. Because the cool thing is if we know our vertices, so we care about our vertices, and then the graphics card, and our perfect lines, and the graphics card cares about the pixels. So basically the rasterizer produces something that is called a fragment. It's just a bunch of pixels that it has to color in, and it figures out how much it has to color these in. So this pixel in the middle, whatever color we're gonna put, is gonna be full on this color. This pixel on the side here that's only slightly touched by the color, so the inside is only this part of the pixel, the outside is this larger part of the pixel. Then it actually, the graphics card is going to take care that whatever color we're going to put is going to be lighter, because it's only a tiny little bit in and mostly out. So they do this for us, and that's called a fragment. So each of these is a fragment pixel. Cool. So now we have our pixel area, and we know that what we have to color in. But now we need to color it in. And hey, look at what's on the pipeline. It's the fragment shader. Again, shader. A shader is a program that runs on the GPU. Okay. And this time it's not a vertex shader, but a fragment shader. So what the fragment shader does is it calculates the color of each of these pixels in a fragment. So we have a program that can figure out what color to put where. One such program could, for instance, also read from an image file and then put the image file into the triangle so that we get an image onto the triangle, like my face or something else. We can also use this to sort of have like color gradients and masking and all sorts of interesting effects. The simplest one, we give it a certain color and it's just going to put it into the pixel. Because then once we have this finished, so this is a function that takes a position in the fragment and some other input that we can provide, that everything is optional except for the position, and puts out a color. And when we have a color into a certain in a certain position, then we have our pixel colored in. So this is much easier than the original pipeline description, because it kind of makes sense. So we have a bunch of points in JavaScript. We put them into memory, into an array, accessible to the graphics card. Then we can have a function that transforms these points as we desire them to be transformed. And then we have a thing in the graphics card that actually takes this information and figures out what pixels to color in, and for each of the pixels that we have to color in, we get a position and we give it a color that we want to see on screen, and then the color appears on screen. Ta-da! Okay, that's not too bad, I think. So let's get coding. Okay, so first things first, we need a canvas. because WebGL is built on top of the canvas, so we need a piece of rectangular space on our website. In this case, it's 500 by 500 pixels, so we have a rectangle where we can draw stuff in. Then in JavaScript, we ask the canvas element for its context, and we need a WebGL context. There was a talk about Canvas 2D earlier in the morning, and that probably used the 2D context. Now we have a WebGL context, which is nothing else than give me all the APIs that you have, oh dear browser, to actually draw things on screen. Okay, sweet. Now we need, remember, we need to put our points somehow in. So here we have some points. So we have this point, so this is 0, 0. I'm using a slightly different coordinate system than you would probably expect. So here, this point is -1 on the x-axis, so this is 0, 0. You go -1 on the x-axis, and 1 up on the y-axis, and then we have -1, 1, and then we have 1, 1 here. So we have 3 points. This point down here, actually, sorry, my bad. We go down -1, -1, and here is 1, 1, and this is 0, 0. Okay, so I always talk about x and y. I have a z coordinate just for shits and giggles, because you could theoretically also do this with the third axis, but I'm ignoring these, so I'm setting this to 0. I could leave it away, but I put it in because it's about 3D graphics after all. So here we have the first point. The 3 coordinates of the first point go here. The 3 coordinates of the second point, which is down here, go here, and the third point, that's this one on top, goes here. And then we create a buffer. So now this is when we create the buffer. We create a piece of memory on the graphics card. And now we have to get the data in. First things first, JavaScript arrays are a little tricky because JavaScript tries to be clever when it figures out the type of memory, and it can mix different types of memory. WebGL does not like this. WebGL wants to have a certain size for each of the items, so we use a typed array, float32 array. That means floating point numbers with 32 bits each number, so 4 bytes for each of the numbers. Okay, and then we put the amount of vertices that we have. Sorry, the vertices array. Now in V, we have a typed array where every item has the same size in memory. This is important. Okay, and then this is a bit annoying. WebGL is using Opengl. Opengl has been around for quite some time, 20-something years, 25 years or something like that, or now even longer, I'm not sure. So it is stateful. What does that mean? Well, it means it has the concept of an active buffer and an active texture. So instead of saying, I want to move this data into this buffer, what you do is you say, hey, WebGL, work on that buffer. And then later you say, hey, by the way, put the data in. And what WebGL understands is, okay, I should put the data into the buffer that I was told to use from now on. So here we are binding the buffer, which means we are saying this is the buffer that we want to work with. Remember, we created a buffer down here. So now we say we want to use an array buffer where we want to put an array in, and we want to use the buffer that we created in Vertex post buffer. Cool. And then, by the way, and this is hilarious because it's just repeating itself. Oh, by the way, we have some data for the buffer, and it's going to be an array buffer data. And here's the data, and we're not going to change it during drawing. So you can actually sort of like optimize for it not being changing. You could use dynamic draw as well if you plan on changing the points, but that's less performant often. Okay, now we have the data in the buffer. Sweet. Now we have to build shaders. That's a more involved process. First things first, as I said, shaders are not written in JavaScript, they're written in a language called GL slang. Okay, fair enough. The cool thing is they're executed in parallel, they don't really have a shared state, which is nice. And then we have the Vertex Shader, and then we have a Fragment Shader, and we have to have one of each. You can't just have a Fragment Shader without a Vertex Shader. You have to have both. Okay. Here's the simplest pair that I could come up with. So here we are taking an array of four values as position. I call it A because it's called an attribute. So attributes are basically variables that get into Vertex Shaders. Only Vertex Shaders. And then we have a main function. Oh, by the way, semicolon, not optional. No discussion. It has to be there. If it's not there, it's going to cry. So here we have our variable that we're going to fill with 1 point at a time. So each point gets filled in here, and it's run in parallel with each point. Then we have a main function, and our results should go into a global variable, into an output variable called GL position. So here what we do is we take a point, a pos, and put it into the output slot, and we are done. That's not much work. It can get more complicated than that, but that's the simplest shader that you can have. Then we have a fragment shader. You remember coloring things in. Also very simple. We have a main function that takes no parameters. Then this is our output value, the fragment color, so the color that we want to put onto the position that we're looking at right now. And we ignore the position where we are right now. We just put in a static bunch of numbers. What are these numbers? Well, they are red, green, blue, and opacity. So in this case, we are putting in green. So all we should get is we take our points form the triangle. We get the same points. Then we color everything in the middle in with green. So we should get a green triangle. Okay. But now, we need to put the shaders somewhere. So how do you do that? We could use strings in JavaScript, but multi-line strings in JavaScript, not that nice. We could put it all in the same line, also not that nice. So the best thing probably is, it's one way of doing it. It's not the best way of doing it. For production applications, there's better ways of doing it, but for the sake of simplicity, I put it in a script tag, but I set the type to text plain, so the browser does not try to execute this. And I give it ID Vertex Shader and the ID Fragment Shader for each of them. So here's the source code, and the source code lives in these script tags. Okay. Wow, okay. Right, now we need a program. What is a program? Well, a program is this pair of shaders that we need. So we need to sort of compile them from the strings that we have. Well, let me rephrase. We need to get the strings from these script tags. We need to compile them, we need to create a program, we need to attach these shaders, we need to link the shaders together, and then we can actually use the program. Okay. That's gonna be a bit of work. Okay, cool. So we create a program, fair enough. We create shaders, one of type Vertex Shader, one of type Fragment Shader. Okay. Then we get the text content of each of the scripts, so this gives us the source code that we wrote for each of the shaders. Then we set the shader source for the Vertex Shader, and then we compile the shader. And then we do the same thing for the Fragment Shader. So now what happens is, these strings are uploaded to the graphics card, compiled on the graphics card. No worries, browsers are clever and cache them, so if they have binary code for your shader already, they're gonna use it, they're not gonna compile it every single time. At least Chrome doesn't and Firefox doesn't, I'm not sure about Safari or Edge. So we now have a binary that can run on, a binary program that can run on the graphics card. Okay, cool. Now we attach the Vertex Shader and the Fragment Shader to the program that we wrote, then we link the program together, and then we can use the program. Oh, finally. So now we have a program that we can use, our pipeline starts to sort of shape up. Now, that is nice, but we need to get our positions, our buffer data, into the program so that it can execute and actually draw something. Okay, fair enough. So here's how that works. You figure out where in the program, in the linked binary, where you have to put these values and how they, you do that by the name. We named it apos, whoops up. We named it apos for the fragment shader for each of the vertices. In the fragment shader they are called apos. We find that location in the shader, we enable that attribute, it's just how it is, and then we basically point our data for that attribute, and then so basically we say, hey program, where should I put something that in the program is called, in the shader is called apos, and then there goes like, so the JavaScript goes, oh, apos is over there, and they're like, can I actually put something into apos? And then the program goes, yeah. And they're like, okay, cool, so here's some stuff that I want to put in, and the program goes, yeah, if you did everything correctly. So that's what we're going to do. And in program code, that looks like this. We get the location of our apos attribute in the program. God damn it. And then we say it's an array, and we want to enable it. So the thing at this location, we want to enable it, and it's an array. And oh, by the way, we want to point you, or this particular location, to an array that has, ignore these last couple of parameters, they are for special cases. The most important thing is we want to put in 3 floats. So that means for each point, we have 3 pieces of information. We have 3 floats, the x, the y, the z coordinate. So 3 pieces, and they are of type float. So now the program knows how much data to actually consume when it runs the vertex shader. Okay, finally. So now that means, with this piece of code, we can actually communicate between JavaScript and the shader, the vertex shader. But how do we communicate with, for instance, the fragment shader? How can we communicate other things? Like, do I always have to do this if I want to just set a simple value, or is there an easier way? Well, there's different ways. So for vertex shaders, there's attributes. Attributes are pretty much the thing that they have to have because they work on something, but they only have like 16 of them, I believe. No, wait. They have 32 or 74, 64 or something, so you can actually put a lot of attributes in, but they have to be, or mostly they make sense for arrays, and they make sense because they basically only, like, it automatically iterates over the array for you, so you don't have to worry about that one. As I said, it runs for each of the points simultaneously, which is nice. It does that automatically for you if you use an attribute. Then there is the uniform. Uniforms are limited in number and are not really automatically iterated or something, so they are more for simpler values, but they can also be accessed in the fragment shader or the vertex shader. And then there's varying, which is a weird thing, which is something that basically comes from or you can use in to produce this value in the vertex shader, and then it's gonna be put into the fragment shader with something cool. If you give it a value, it basically sort of multiplies it with the position that it is in the fragment. So that's actually quite nice. We're gonna see that in a bit. All right, and now we draw. Finally, we draw. God damn it. So remember, it has this concept of the active buffer and the concept of the active program, because we said, here's my buffer, it's the active buffer. We haven't undone that yet. It's our vertex buffer is the active buffer, and our program is the active program because we have no other program. So the only thing that we need to do is say draw arrays. And then it basically knows that it has to use the active buffer and the active program to do this. And we say, please draw it as triangles. Start with the 0th element and do it 3 times. So we have 3 points with 3 values each. Please do this. And then we keep on going this in a loop, doing this in a loop, and then we get a triangle. And then it looks like this. And the code is available. I had to do it in so many slides because it's a lot of code and you would not be able to read it. Basically, I wouldn't be able to read it from this distance. So this is a green triangle, even though the colors look weird in this environment. Well, congratulations. This is your first WebGL program. It's an amazing program, and it's probably, or very likely, the worst demo ever, right? It's like, wow, we wrote a lot of code to get a green triangle. Why did we bother? Well, because this is the minimum amount of stuff that we have to do to get anything with WebGL on screen, unless we use a framework. But the cool thing is, it's not like you have to do just as much more stuff to get something more fancy onto it. No, no, no. This is like plateauing. So it gets more involved the more stuff you do. But this was the hard part. I actually brought you through the hard part because this is like all these moving targets, all these shaders, all this kind of stuff. We have done this, so we can now start actually doing more interesting things with it. So let's have a look at improving this one. So, because I don't trust the Wi-Fi, I have a local version running. Isn't it amazing? Wow, a green triangle. I'm dying of happiness. So this is not a very interesting example. So let's improve it slightly. How about we get ourselves a separate buffer, a new one. So let's say I put in some colors. And as we know, colors happen to also be RGB, so I say the first corner shall be red. Or actually, why do I even bother with the points? So 0, 0. And the second color should be, the second corner should be green. And the third corner should be blue. Okay? And now I put these into a buffer as well. And I call this the wonderful C buffer. Float 32 array, colors. And then I say, oh, I also need I need to create that buffer. Color or vertex color buffer, vertex color buffer equals GL create buffer. So I create myself a little buffer. I put the colors into a typed array. Then I say GL bind buffer. So I bind the buffer as the active buffer, and it's an array buffer, and it's the vertex color buffer, and we say GL buffer data. So we put the data into the array. Don't even ask me why I have to say twice that it's an array buffer. That's just how it is. Just deal with it. Also, does not change in between drawings. We do not touch this because our shader does a great job. And and now we say, oh well, we can reuse attribute location, I guess. So we get the attribute location in the program that we call a color. And we enable this one, enable vertex attrib array, attrib location, GL vertex attrib pointer. So now we point the data in the into the right spot. Actually, beforehand, so this is where it gets annoying. So actually, wait a minute. Can you even read this? I'm not sure if you. I'll make it larger. Sorry, I should have checked. I'm so in here. Let's see if this is more readable. Is this better? Okay. So what I did is I created a second buffer. I put some color data in, and I put the color data for red, green, and blue in. I put the data into this buffer. Now the problem is that remember the concept of the active buffer. So when I did this down here and said like point to this particular data, I pointed it to the active buffer, which is now no longer the vertex position buffer. So I have to say bind buffer again, so that I get the right buffer, and I'll just copy the line because I can't be bothered to type that much right now. So now we get the actual buffer that we want, and then we get the other buffer back. Vertex color buffer. And we look for the variable a color in our vertex shader. Okay, and then we put the data in, and it also has three bits or three numbers per each entry. It's a float, and we don't care about certain optimizations because we don't really need to. And then because the drawing needs to use the vertex buffer again. Wait, I copied that one, so I can probably just yes. So we need to make this the active buffer again. That's not very efficient, but let's just follow me on this wonderful round. Actually, changing buffers or activating buffers is not that expensive, so that's not too bad. So now we also need to change our shader a bit because we want to use this information, right? So we're gonna go. We have vectors. Screw it. A color that we want to use, and here's the thing. Let me quickly cheat because now I kind of lost track where I was doing, because this is what you're gonna get at the end. Yes, but oh yeah. Thank you very much. Yes, right. So what we want to do is we want to have this one basically assign each corner of our triangle a color, the color that we already prepared for this. So the one corner is going to be red, one color is going to be blue, one color is going to be green. And what we can do with varying... yeah, so theoretically I could have vec3 on both of them, but this variable has the type vec4. So it forces me to have a vector 4 because it is particularly made for 3D graphics. And in 3D graphics, it's actually convenient to have like a fourth component, because then you can do matrix transformations in 3D. So this is kind of what I could. You are right. What I could totally do is I could do this, make it a vector 3. The problem is this return here has to be a vector 4. But the cool thing is GL slang has this nice feature that allows me to say I make a vector 4 by taking a vector 3 and appending one more element, right? So I can totally do that. It's absolutely possible. I just didn't want to do it because I'm like, then I have to sort of explain exactly this, and I kind of wanted to skip over this one, but okay, now we did. So we can actually make different thingy. So we now also set the precision. So we say this is high precision value that we're gonna do, and it's type float, and we're gonna call it a v color. No, sorry, this is not float. What the hell am I talking about? This is not float. This is vec. Jesus, I lost my flow. This is vector 3, and then what we can do is we can say, for each of these vertices, we're gonna set this value, this original value, v color, by just assigning a color to it. And then, down here, we can say varying vec3 v color. So we can access the variable from the other shader in this shader. And by doing so, I can then use this. It's the same magic that I just used, so that we get the alpha channel to be opaque. Okay, sweet. So theoretically, if I did everything correctly, we should now see colors. We don't, because my shader program is incorrect. Program not linked, program not valid. I love it. So my program is invalid, and I'm not entirely sure why right now. Okay. I'll quickly cheat by looking it up again. So where did I go wrong? I think that is one possibility, but I actually, because I was wondering, I think colors have to have high precision because they're gonna be, no, that's not the problem. There is a way of getting the debug output that I can never remember this one, so I'll quickly check if I have it in here, because I should probably have it in here. Yes, this is the one. Ha! So, I'm gonna get the compile status because I can't remember why it failed. But this is actually good because you're gonna get to see how to debug this kind of situations, because you're gonna be in this kind of situations all the time. Shaders are fun. So if it's the compilation error in the Vertex Shader, or if it's the compilation error in the Fragment Shader, we're gonna get an alert. Fragment Shader. Because nothing is better than actually getting an error message. Ha! Fragment Shader, shader program is not defined. What? Oh, because I called it differently here, didn't I? Didn't I just call it program? Yes, I just called it program. Damn my eyes. So, program. And it was the Fragment Shader, wasn't it? And I should get this one, obviously. So, okay. Let's run this again. No precision specified for float. In line 2. I knew it was something to do with precision. Because there's like high precision, low precision, and medium precision, and it's kinda spiky about it. So it's in the Fragment Shader, so I should say varying high precision. Yeah, it was a precision issue. Okay. Okay, now it, right, now the shader is okay, but it doesn't draw anything anymore. I'm sorry, I lost my flow. Damn it. But that's not an issue. We're just gonna cheat and pretend everything is fine. So the difference is in the shaders. And what did I do differently here? I just want to quickly check if I oh. Did oh, but that's okay. That is okay. That is okay. That is okay because I change it to a vector 4 here. For color. But I use vec3 here and I use vec3 here, and that should be okay as well. No, wait, you're, oh god, I think you're right. No, you know you're not. Because this is vec3 and this is vec3, so this, and there's no compilation error. Let's just see if there's a linker error as well, because it could basically fail when I link the program as well. And if I'm not lucky. I do not have the error catch thing for linking error, so probably it's a linker error. But what I could do is I could steal, if only I would know if it's the, so here I use vector 4, which is fine. but I also use it differently. So let me see my main.js again, because we have still enough time to do this. So my colors are certainly 3 values. That is good. And I bind them. Yes, correct. And then I load my shaders, I compile my shaders. I enable the vertex. Here I'm using 3 as well, so the amount of data that gets transferred is correct. All right. Attrib app location. This is a good one. This is actually an interesting problem that I haven't prepared for. I'm doing this correctly because I'm setting the opacity to 1.0, so this is all right. So what happens when let's just see if the shader's compiled correctly by setting it to pink, and then it should give us a triangle again in pink. Aha. Index out of range. Dun dun dun. Enable vertex attrib errors. Okay. Line 72 and line 73. So there's my problem somewhere. Maybe I shouldn't have reused the variable here. So I'm gonna call this attrib location 2. Wow. So I bound this one. I bound this one. So it says out of range, which is strange. Oh, that rhymed. Enable index out of range. That means that I'm not having enough items in it, but I don't understand how that happens, because I certainly have 3 items each here, and I copy them over into this wonderful thing, and then I put the data in. What's this problem? Anyway, so I know that this one is a JavaScript problem, so this is nice because it's not that bad. So I can probably steal from here. So I'm getting the location, GL attrib location. I'm setting the data, and the data here is slightly different because I think I use, yes, for colors here I use a different format. I also have the angle, the opacity in here. Maybe the opacity is 0, but that's alright because I say that I only want 3 values, and that should be okay, but somehow it's not, and I'm not entirely sure why. Anyway, the thing is, I'll copy this over. Really, there's no point in not copying it over. Sorry? So, yeah, it uses the same thing, and now the buffers do not work anymore. And anyway, you see the result here. So let me walk you through the code. It does the exact same thing that we did beforehand. However, it loads the colors correctly. Apparently, damn my eyes. The code is online, so you can check it out. And what it also does is it changed the Vertex Shader. So I'm going to show you the changed Vertex Shader. What we're going to do here is important because it's a new concept that I haven't shown beforehand. So in the Vertex Shader, which is this beauty here, first things first, I wrote myself a little matrix. So this is a matrix that is the rotation around a certain angle. So this is how it has to look to actually rotate it around a certain angle, okay? And the angle is a uniform. So here we say uniform float U angle, and then we use this to actually rotate the thing. And then we multiply the position, X, Y, Z position of the vertex using this matrix, and that means that we are getting the rotated points for this particular value. We do not re-upload the buffers. We do not touch the data. All we do in JavaScript is we call this one function that is called uniform1f. So all that JavaScript has to do in main.js is to set this particular value. Yes?
In color buffer you used only 3 values, but for GB it must be 4.
Really?
Yeah.
Oh, because it's an attribute. Let's see if we can. Let's see if that solves the problem. Then that'd be hilarious. Because I'm pretty sure I'm pretty sure it has to be 4 values. I'm not sure why I resisted. A lot of people pointed that out. I'm very sorry for that one. I just wanted to test you. No, that was the correct value. Okay, so vector 4, and then obviously this is a vector 4, and that makes the code here slightly easier because I can just use the vector 4 here as well. Bam, v color, save. Oh well. I may have broken something else now because I entirely lost. I'm very sorry. The code is online. I'm going to put it right on the slide because I think I forgot this link. So slides are online as well, so you can easily click here. And then with a bit more code, you have a rotating, three-dimensional rotating triangle, which is nice. Oh, better. Sorry for the interruption and the loss of flow. Anyway, so as I said, everything that we did here in this talk was the deepest possible dive to get you going with the bare details of how these numbers work on the very low level. Good news, you don't have to care about this kind of stuff most of the time because there's brilliant frameworks such as Three.js, Babylon.js, and Stack.gl. These three libraries or frameworks, whatever you want to call them, helps you to actually develop things without having to care about the small little gritty details. So they do all these kind of buffer work for you, and then you can spend time actually building your content and importing 3D models and building awesome games or building awesome applications. And last but not least, you can then spend time and focus on optimizing the bits that aren't good for you. For instance, writing your own shaders rather than having to deal with triangles and stuff. So check these three out. Pick the one that works best for you. None is better than the other. So you're ready for WebGL. The hard parts are now lying behind you. So you are ready to get going and get into space using WebGL. And with that, spasiba. Вопросы?
I would like to ask regarding mobile devices.
Well, sorry.
Yeah. So about responsive design and mobile devices, how does it work with that?
So that's a tricky one. It does work on mobile devices. So all browsers on mobile devices nowadays have WebGL support. Responsive design is a bit tricky, but the thing is, you have a canvas element, so you can actually scale that nicely, and your coordinate space is the same size, so you don't have to worry about that much. You want to resize your coordinate space if you want to do sort of like very tiny small things, then you want to resize it, but unless you don't, you're gonna have a zoom functionality. So that's what we're gonna do. So we're gonna give you the exact same results as it would be on desktop, except for some performance optimizations, but basically just smaller, and then you can zoom in or out as you desire. So it's not a problem.
As you said on when you start your application. Yeah.
Exactly, yeah.
Got it.
Awesome. You're welcome. Other questions? Well, there's going to be the after party, and I'll be around, so I'll stop talking and leave the stage. Oh, one more question. Aye.
Yeah, sorry.
Sasha.
How often in your daily job you need to actually dive into WebGL rather than just using the framework that I've already written?
I would love to say not that often, but that's not true.
What's the cases actually?
So normally you don't, but when you start doing visual improvements, then you have to do that quite often. So for instance, we do what's called a blooming effect that makes light more diffuse, more nice, because light, when you calculate it, is mostly like very sharp. So like if there's a light ray, then here's all the light and here's no light. And that's not how reality works. Like, if you have a spotlight that shines on someone, you have all the light, you have mostly all of the light, you have some of the light, you have a few bits and pieces, like a few photons, and then you have nothing. So this kind of calculations actually require you to go around the framework every now and then. It gets better and better, but it still needs some tweaks for us sometimes. Yeah.
Thank you.
Has been my pleasure. Thank you very much.
Thank you, Martin.